I'm live. Okay, so now we're recording. So once again, the mechanism questions are usually super simple. It's one of those things like, did your teacher teach it to you? So while there are 3-step and 2-step mechanisms, the AP almost always tests 2-step, which is, or sorry, 3-step, no, 2-step, which is 3 humps. So AP almost always tests 2-step, 3 steps with 2 humps. Does that make sense? Okay, and I'm going to show you a worksheet they published about a decade ago. It's pretty rough. It's just like a scanned PDF because they published a PDF of a bunch of mechanisms. Again, the key thing about mechanisms is every step will be classified as slow or fast in comparison to the slowest step. The slow step is the only thing that determines the rate law. Okay. The mechanisms together will match the stoichiometry, but the stoichiometry doesn't necessarily match the rate law. Okay. So take a look at this reaction. This is 2 molecules of NO2 reacting with a single molecule of F2 to produce 2 molecules of NO2F. This reaction is used a lot on the AP. Okay, so slow step determines the rate law. So that's one step. In the first step, a single NO2 molecule reacts with a single F2 molecule to produce NO2F, but just one, and an F radical. Okay, that F radical is something that cannot exist on its own. You know, we have to have F2 or F minuses. So the F radical cannot exist on its own, but then that F2 or F radical then reacts with a second NO2 molecule to produce the second NO2F molecule. So can you see how this plus this equals that? So this F star is called an intermediate. It is something that is created in one step, but then consumed in a future step. It's not something that exists on its own. If you were to freeze the reaction in time, that intermediate does not exist. You can't, basically, it does not, it's basically something that is created and then consumed to make something happen. Okay? So if you were to diagram this reaction, well, with what you know right now, how many steps or how many humps would this reaction have? It would have a single hump, exactly. So if we were to diagram this, I'm going to make this exothermic. So I'm just going to pretend that it's exothermic. Maybe it is, maybe it isn't, I don't know. But we're starting with 2 NO2 plus an F2. So far so good? Those are our reactants. And we know we're going to end with the products. Now, if this is exothermic, we're going to say this is energy, and this is called a coordinate. You can kind of think of it as time. The problem is if we call it time, that would infer that it's like per second. So it's just like progress. You can think of the reaction as this is the progress of the reaction. We can pretend it's time, but time gets kind of icky because time is actually a unit. We don't have anything. Okay, so this is exothermic. Should I place the products higher on the vertical axis or lower on the vertical axis? If it's an exothermic reaction.
Lower.
Lower, okay? The overall energy state's gotta be lower. So again, let's say this is 100 units and this is 50 units. The delta E would be 50 minus 100, ending, starting. So changes are always where you ended minus where you started. So the energy would be negative 500 units, or negative 50 units of energy. Again, negative energy is exothermic. Remember that from last April, or last April? Okay. Energy gets its own unit. It's unit, it kind of gets its own unit. It's unit 6 and a little bit of unit 9. But we'll get there. Okay, so back to this. So the reaction is going to start with our reactants. It's going to end with our products. And get rid of these numbers because they're not important. They're made up. The important thing is exothermic. And we're going to end with 2NO to F. Okay? So now we're going to draw a hump. There's a hump, just one. And at the hump, what we have is NO to F plus F star. I read it, almost done. And then that NO2, that F star, so this reacts with plus, sorry, yeah, okay, so let's just, I need more room, and I also need a different color. Let's use that. So the end of the first step, we have NO2. So this reaction is the NO2 plus F2, and it's going to produce NO to F plus F star, and then the F star, let's try that again. Then the F star plus the NO2 is going to produce our product. Okay, 3 steps is going to give you 2 humps. 2 steps is going to give you 1 hump. The overall reaction, if it's exothermic, the products are going to be lower. If it's endothermic, the products are going to be higher. Okay, now we're going to talk a little bit later. We're going to show you that each step can be classified as exothermic or endothermic. Each one. In this case, you would realize that the first step is what? Endothermic, because the intermediates are at a higher energy state than the reactants. But then from going from the intermediate to the product, that's exothermic, and it's more exothermic than the first step is endothermic. Is that clear? All right. Questions so far? Yes.
How do you find rate order?
Good question. You look at the reactants in the slow step. So the reactants in the slow step are determines the rate law. And again, you can't just look at the stoichiometry. You need data or someone that has to write the mechanism out for you. So right here, we would say rate equals K, because K's always got to be there. What 2 things are the reactants in the slow step? NO2 and F2. That is the rate law. It's first order with respect to NO2 and first order with respect to F2, second order overall. So you notice this rate matches the reactants of the slow step, but it doesn't match the stoichiometry.
How do you know it's first order?
Because there's only one NO reacting with one F2. So another way to think of this is NO plays a singular role, NO2 plays a singular role, and F2 plays a singular role. If there were coefficients in front, that would mean that molecule plays a greater role in the rate. So if there was like 2 NO2, then you'd have to put an NO2 up here because the 2 NO2 would play a greater role in limiting how fast the reaction goes. So one of the weird things that a lot of people think about, or that we need to talk about, is rates are usually defined as how fast the reaction goes. It should really be defined as how slow the reaction goes, because the rate law is based on the slowness of the reaction. Does that idea make sense? So NO is singularly limiting the reaction. Sorry, NO2 is singularly limiting the reaction. F2 is singularly limiting the reaction. If there was a 2 in front of the NO2 in the slow step, Then you'd put a square above the order, and you'd say it's second order with respect to NO2 because NO2 is slowing it down even that much more. Is that clear? And it's kind of weird to think of like, it's how fast the reaction goes. It's actually how slow the reaction goes. Rate laws are how much you slow the reaction down. Okay, is that clear? Any questions? So, the rate law doesn't match the stoichiometry, but the mechanism does. If you look at this, we have an NO here and an NO here. Those two, we have an NO2 here and an NO2 there. Those two NO2s become the two NO2 up there. We have an F2 there. That single F2 becomes that F2. We have a pair of NO2Fs that become up there, and then the intermediate cancels out. Intermediates will always cancel out because they cannot exist. Okay, how are we doing? Good. Give me a thumbs up if you're with me so far. Wave your hand around if any of this doesn't make any sense. All right, moving on. Boop. Whee! Whee! There we are. Okay. So take a look at this guy. This is a single mechanism for a reaction. I don't know what the end product is. That's a single reaction. So just looking at that singular piece of the mechanic, that single step, can you determine what the rate law is going to be? The answer is because you will only have one slow step in a mechanism. Because even if you're like, well, that step takes a second, that step takes a tenth of a second, those are both slow. But we say slow and fast, only one step is slow. Everything else is faster than that step. So we only look at the slowest step, because slow and fast don't mean anything in the grand scheme of things. They only mean something with respect to the other steps. The slow step could be super fast. It could be a nanosecond, but it's still slower than all the other steps. So that's what limits the reaction. Okay, so if you look at this, you'd say, all right, yeah, I can definitely write a rate law because it tells me it's a slow step. And you can only have one slow step, so if it tells me what it is, then the rate is pretty simple. It's just going to be rate equals K. What are the reactants of the slow step?
O3.
O3. What is its order? 1. And?
NO2.
And NO2. And what is its order?
1.
1. So we would say, based on this mechanism, the overall reaction, whatever it happens to be down here, is going to be first order with respect to ozone and first order with respect to NO2. How are we doing?
So if there's like a 2 in front of like O3, would it be second order?
Yep.
And
Yeah.
3 would
So-
be third order?
Yep. If there was a 2 there, there'd be a 2 there. And yeah, if there was a... Technically speaking, reactants could mathematically be third order. I just can't think of a specific instance though where that's ever going to happen. So only thing I've ever seen is second order, first order, or first order, second order, with an overall third order. I've never seen a reactant that is third order, but technically it could exist.
What would be 0th order? Like,
If it's 0th order, then it wouldn't be in the slow step. So this is how I think about orders of reactions. It's like you have, remember, to get a good collision, to get a reaction to happen, like we said at the very beginning of this unit, you have to have enough energy for the two parts to collide. Then you have to have the correct orientation for the two parts to collide. If something is first order, it's like, remember we talked about Legos? It's like Lego brick. I should just get some Duplos up here, but they're in the back. Anyway, just imagine, I got a Lego brick with the studs facing that way, and another Lego brick with the studs facing that way. The orientation is good, and they come together with enough energy, they will stick and create the product of 2 blocks. Huh? Make sense? Okay, so that's first order. They're both involved in the reaction. Second order would be 2 blocks have to come together and before they then react with a third block. It's kind of like, I really just need to take a look at Legos. Imagine this is your looking face on. So there's our studs. There's our studs. And then they have to go into a socket that looks like this. So this is our first, this is our reactant, this is our reactant. This would be second order, this would be first order. In other words, these both have to orientate properly, which means they have a double, if you will, a double effect on the rate slowiness, the rate law. Does that idea make sense? So the reason that a third order reaction can mathematically happen, but practically won't, is because you would have to have three molecules of the same type, all coming together to react with that other piece, which would be super unusual. Just geometrically, it would be very difficult to do.
Can you have a fourth order?
Well, again, to have fourth order, you would have to have four molecules all oriented properly as they react with something else. It's just geometrically, I don't see how that could happen. Does that make sense? It's so crazy unlikely. I mean, imagine like you have two hands, right? You're putting Legos together, Lego, first order. That's how we work. Imagine if you had second order, that means you have to have two hands and somebody else has to have a hand too. Third order means you and someone else all have to react with one block and somebody else has to have a third block or a fourth block in that case. So it's just highly unlikely. I mean, mathematically, you can conceive of it, but I can't think of single circumstances that would exist. Let's move on.
Just go to ninth order reaction.
Ninth order reaction would mean you have 9 pieces all interacting at the same time. Okay, so that's our reaction. Now, that's our second mechanism. Okay, our second step of the mechanism. So first step is that, second step is that. What's going on here is O3, ozone, is reacting to NO2 to produce NO3 and O2. That is slow. Then NO2 is reacting with NO3 to produce N2O5. That's fast. What is the overall reaction? See if you can scribble it down. Scribble down what the overall reaction is, and I'm going to show you something kind of neat. So go ahead and do it on your own. Scribble it down. What is the overall reaction? Squish the two things together, cancel out what cancels out, and then, yeah, we'll see what the overall thing is. To get all the pieces, O3, NO2, NO2, NO3, NO3, O2, O5. Okay, so all the pieces.
So it produces N2O5 and then O2.
Yep. So you see the intermediate? The NO3 gets produced and then consumed. And when you squish them all together, there's the same number of NO3s here and here. So those are our intermediates. That is our intermediate. So then we write down what's left over. And what's left over is O3 plus 2 NO2 yields a single O2 plus N2O5. Is that balanced?
Yes.
Two nitrogens. 4 and 3, 7 oxygens. 5 and 2, 7 oxygens. This is our balanced chemical equation. All right, questions? See in the puzzle? We're good?
Yeah.
We're about to turn a corner. Make sure we're good. Okay, let's do one more practice just so we can make sure we're all on the same page. So go ahead and bang this guy out. Yeah, there you go. Identify the overall reaction, identify any intermediates, identify any catalysts. A catalyst is something that is both a reactant and a product. Something that is at the beginning and at the end. So bang that guy out. Do you see any intermediates? Do you see any catalysts? There we go. Write the rate law. Good. All right. Wait, did it? What? Wait.
I'm confused. Don't they produce like? They don't produce. Never mind.
Okay. Overall reaction?
2H2 plus 2NO
2H2 plus 2NO,
goes to 2H2O plus
2H2O plus, what was the last part?
N2.
N2. All right. 4 hydrogens, 2 nitrogens, 2 oxygens, 2 oxygens. It's certainly balanced. Cool. Did we agree that's it?
Yeah.
Right. Rate law. So the rate law, again, when it says the rate law, please make sure you put all parts in there. Rate equals blah, blah, blah. Do not, well, that's holy, start with a K. And don't just give me the orders. When it says rate law, write the entire rate law. Okay, so rate law, rate equals K. What do you want to put in the rate law?
H2.
H2, and how many, what's its order?
Aren't they both?
First order? And what else?
NO squared.
NO,
Wait,
and it is second.
because it's 2 of them.
Because you got it.
There's 2 H2.
You need that.
There's
Oh,
one
and
H2.
there's the
Are we happy with the rate law?
Yes.
Next, intermediates.
N2O.
N2O. You make it, and then you consume it.
You don't have that. You add hydrogen twice, right? You add H2.
Yes. So
Wouldn't that affect the rate law?
Only the slow reaction.
The rate law.
only the slow step matter. Basically, it's like back to our thing with the guy with the sweater. Only the slow step plays a role in slowing the reaction down. All right. Give me a thumbs up if you're comfortable with this. Okay. Now, if you ever have something that is both a reactant and a product, you have a catalyst. So take a look at this. In this case, this is very similar to what we did earlier. We're breaking down hydrogen peroxide. So hydrogen peroxide reacts with the iodine ion. Great. And it makes the OI ion. I can't remember if that's iodate or what, but anyway, it makes that, but then it also consumes it. So OI is an intermediate. But take a look at iodine. It's there as a reactant, and it's there as a product. So it is a catalyst. Catalysts do show up in the rate law, which is really kind of funky, but it just happens. Okay, so overall rate, first do the rate law first. The rate law, based on the slow step, okay? Slow step needs H2O2. And the slow step needs the iodine ion. Okay. That is the rate law. It's all the parts of the slow step. But here's what's funky. When you do the, can I do blue? No, it's not blue. Let's not do blue, let's do green. When you do the overall reaction, you got H2O2. Weird. That was strange. H2O2. You got two of them in the mechanism. Two. And then you got two H2O. And a single O2. And look, this is our basic hydrogen peroxide decomposition that we've used a million times. The iodine isn't in there because it's a reactant and a product. You could write in the iodine and cancel it out if you want. But it is a catalyst. In fact, most of the time, if you went plus I minus, no one's going to care because it's there. But it's technically not in balanced chemical equation. That's a catalyst. All right. How you feeling about this? Good? Any questions?
It's included in the product, so it wouldn't be in the equation.
So it starts as a reactant,
Yeah.
goes through the process, and is remade as a product.
Oh, okay. It's the same.
Wouldn't a catalyst make it second order?
You mean the overall reaction?
Yeah.
Yeah.
Wouldn't that make it slower?
Yeah.
So a catalyst makes the reaction slower.
No. The catalyst makes the reaction faster, but the catalyst does play a role. In other words, this mechanism that has the catalyst present is a certain speed. Get rid of the catalyst, and now H2O2 limits the reaction, but how fast it is irrelevant. Does that make sense?
Yeah.
So, I mean, maybe this reaction takes a millisecond, but without the catalyst, it takes a second. The rate law tells us nothing about in our world life, how fast something goes. Okay. Is that kind of clear? It's wonky. It's like, yeah, catalyst, like, what does make it? Yeah, catalyst will make it faster. That's just a fact. But how fast in absolute terms, we have no idea. We're going? It's a very good question. Okay. Moving right along. Okay. This is an actual AP question from the reaction mechanism workbook. And they used to publish these workbooks. They do one workbook per unit. I haven't seen them in years, but here we are. Okay, so take a look at this step. First of all, how many humps are you going to see?
There's 3 steps, so 2 humps.
Yep, 3 steps, 2 humps. Okay. So you can see 2 humps, and you look at this and say, all right, I have an elementary step. That's what they're called, elementary steps. The second step is the slow step. But what's weird about it is the slow step has a reactant that's an intermediate. You cannot have the concentration of an intermediate. An intermediate gets created and used up entirely, so it cannot have a concentration. So what do you think we should do instead? So first of all, when you squish them all together, that's what you get. 2NO plus 2H2 makes N2 2H2O. Can you see that when you squish them all together? Now here's what you do if your slow step is not the first step. You say, all right, my rate, I think I actually explained this in the next slide too, is going to be K and N2O2 and H2, and then bells go off and you're like, wait a minute, this is not in the reactants. So this cannot exist. But what can exist is the thing that makes it up. That. So you replace this and you say K prime, and I'll get to the prime in a second, is NO second order, and then we bring the H2 down. So we replace the N2O2 with NO second order, because that's what makes it up. Is that clear? Now, why did I do K prime and not just K? Oops.
Why don't you start with the N2O2?
Because I'm using the slow step. Oops, the reactants of the slow step.
Oh, that's right.
So N2O2 cannot be in the rate law, yet it is a reactant in the slow step. So I cannot, a bracket literally means concentration. It needs to be measurable. Shoot laser through it, measure its absorbance. So it needs to be there, but it can't be there. You cannot measure an N2O2 concentration because it's an intermediate. But the intermediate is made arbitrarily fast by two NOs. So you would replace the N2O2 with an NO second order. Now, why do I use K prime and not the original K?
Because it's not the slow step.
Because it is the product of K2 and the inverse of K1. In other words, it's K2 moving this way, and it's K1 moving that way. Let that sink in for a second. It is the product of the K2 for the second step, which is a slow step, but it is the inverse of K1 because this reaction has to be flipped over. Because you don't put N2O2, you put 2NO, but we're moving that direction to make it. Does that idea make sense? Now, the next slide has the actual mathematical mix that I've never seen tested. No, that's not true. I've seen it tested one time. And everybody in the room got really angry. Okay, so here we go. So this is exactly what you saw. Now, if something is fast, like that, it will always be in an equilibrium. Don't worry about equilibrium, we'll talk about it next May. Or talk about it next March. Okay. So first, rate 1. This rate is K1 NO2, but it's fast. Slow step is K2 N2O2 H2. Slow step. Third step, which is irrelevant, is K3 N2. Again, it's not important. But here's the thing. The K is a mathematical number. It's a number with a value and a unit. So what you have to do is take the inverse of the K, see it says K1 reverse, so it's 1 over K1 reverse, and plug it all together, and that's what you get. You replace N2O2 with what is N2O2. This is N2O2. Can you kind of see how it's KNO2 is KN2O2? If you can't, don't worry about it. This is also one line. I think it is. I uploaded this, right?
On Canvas.
Yeah, is it on, did I put this on Canvas?
No, we have the AP Chem solutions. Yeah.
But at the very beginning of the unit. Did I put it in the unit, at the very, very beginning of the module? Sometimes I forget.
The
Irrelevant. Okay, so moving on. So again, I've only seen this tested one time, and it was maybe 1 or 2 points. And hopefully they learned their lesson. They're like, this is too complex for high schoolers. Just in case they do. So bring the 4s and the 5s, I understand what this is. Cool. All right. All right. Questions? Let's look at some exercises.
Are we expected to memorize that?
Heck no.
Okay.
Too many letters.
The only thing I would recommend, again, I would say there's almost no chance of them doing this again, but they always have something to separate the 4s from the 5s. And should you find yourself in that scenario, understand that if you have, this is what you need to take away from this. If you have an intermediate in the slow step, replace the intermediate with what makes it up. Don't worry about the math. Okay? Because they're not going to actually give you any numbers for K. You just need to understand that the K you use is not only the K for the slow step. It also includes the inverse of the K from the previous step. Because the components of the previous step replace the intermediate in the slow step. Yeah? Don't worry about it. Just realize if you, the most important thing is if you have an intermediate in your slow step, replace that intermediate with what makes it up. Don't worry about the math at all. Because there won't be. Okay. Other questions? Oh, my brain is warm. I have a warm brain. Okay. Am I bleeding? No, no blood.
Oh,
Yeah.
There's survival lab. Mechanisms today. Ooh, we have ABCs tomorrow. Okay. So this is the author's extra crazy wordy, what we just talked about.
Whoa.
Yeah, you can see why I reduced it down into PowerPoint, because I was like, you've got to be kidding me. But let's look at some actual exercises we worked on. Oh, did I see what? Did I make a note on 2, 6, and 7? Okay, so, oh yeah, number 2, this is great. Number 2 is an excellent one. I think this actually is an AP question. So take a look at number 2. Oh, by the way, really obvious indication something is a intermediate is if it cannot exist.
What do you mean count?
Like CL.
CL.
Oh.
Physically.
Physically cannot exist outside of a plasma, so that's why it's there. Again, we call it a radical. Sometimes they'll even give you a star. In this case, they didn't.
For each of the steps?
Yeah, the rate law for each of the elementary steps. The author puts that in because that used to be in textbooks. AP doesn't do that anymore. They only care about what's important, and that's the slow step. But they do, again, this is an artifact of before time that nobody tests anymore. So overall reaction?
2NO2Cl
NO2Cl.
goes to 2NO2 plus Cl2.
2NO2 plus Cl2. Are we happy with this? Okay, cool. Intermediates, we talked about this.
Cl.
Yeah.
The non-existent.
Boop, boop. I'm going to ignore the elementary steps and just go with the
First order.
rate of reaction, and it is first order. So the slow step, what are you gonna, again, we're gonna write the rate law. We're gonna start it always this way. Then we're gonna say, what makes up the rate law? What's the first thing I'm gonna use? NO2Cl. What order would you like it to be? First order. And the other thing you're gonna add?
How do you know?
Is anything else added? Nope. There's only one thing. There's only one reactant, the slow step, just that. So that's it. First order with respect to NO2Cl, first order overall. And that's the lingo you should use. First order with respect to this, first order overall. Second order with respect to this, first order with respect to this, third order overall.
What happens when you have like let's say you have like 2 reactants for rate law, and they each have a coefficient to make it balanced. It's like 5 and a 7. How do you determine the order then?
12th order.
Yeah, you just add them together.
Wow.
Yeah, but again, that's never going to happen. I have never seen the AP test anything but first and second order, and the most exotic was a first and a second together. Usually it's just a first, or just a second, or 2 firsts.
They're gonna do 32,
How does
like
it-
64.
How does a 2 multiply get to a 2 in the exponent? Like, how's the multiple go to the exponent?
Again, because the exponent just represents how many there are. It's not like I'm not.
Are you, if I understand you correctly, are you upset that
How's like the 2 as a coefficient
That
translate to?
and that don't match?
No, but like when it's like you have a 2 in the coefficient and that's second order, how's that translate to the second power?
Again, reaction kinetics, we like to say they're how fast the reaction goes, but they're really how slow the reaction goes. So if something is, if some reactant is second order, it means it plays a larger role in the reaction. And we like to say, well, if you double the concentration, it doubles the speed, but or quadruples the speed. But it's usually, you got to think about the other way. If you have the concentration, you quarter the speed. In other words, because if you have 2 reactants, a good example. Yeah, okay. So let's say we got rate equals kx to the second order, and then whatever else. So the reaction is 2x plus 2y makes 4z, okay? So in this reaction, y does not limit the reaction at all. Maybe it's a proton, maybe it's an H+. Okay, so it doesn't limit the reaction at all. It's here, it's easily accessible, it's got a lot of energy, it bangs into things, no problem, it doesn't play a role. It needs to be there, but it doesn't play a role. X, on the other hand, plays a role in the reaction. Anything you do to X, you do to the rate. And we like to think about, oh, I doubled the concentration, I doubled the rate. But keep in mind, it's how slow something moves. If I have the concentration, I quarter the speed of the rate, or the speed of the reaction. Because that concentration change affected the reaction twice. Half-half. Does that make sense? So when you have a second order thing, it's playing a doubly destructive role to the speed of the reaction. It's slowing it down twice. Does that make sense? Again, I know it's really wonky because we like to think of things as more makes it go faster. And that's kind of how we teach it. I doubled the concentration, I doubled the rate. But what really happens is its loss in concentration plays a larger role in the slowing of the reaction. It's exponential. Yeah.
Can we look at number 7?
That's a great idea. Let's do that. Number 7.
Legos.
Okay, elementary steps involve 3 or more reactant species are very rare. Things like this. Didn't we just talk about this half hour ago?
Is it just a Lego analogy?
Yeah. If you have a third order, the chance of getting 3 things all oriented properly is extremely low. Alexa, stop. Okay, are we comfortable with what we're doing now? Let's call it a day. Okay. Bye, Hazel. I hope you enjoyed the video.
The DMV.